point. You guys did up to 70. Does anybody have any questions on stuff? Aria?
You do 29.
29? The population of Jacksonville, Florida was 736,000, was increasing at a rate of 1.49% each year. At that rate, in what year will the population reach 1 million? So this is a population model. So 736,000 plus 1 plus, or times 1 plus 1.49 over 100 to the t. And we're solving this then when P of t is equal to 1 million. So calculator time. We'll have 1 million here. Have my model over here. Clear that out. Reset my window 0 to 1. That's, or 0 to 100. That seems fine for time. We'll go 700,000 to 1.25 million. That seems good. So there's my 1 million line. What did I do? Oh, ha. Forgot some zeros there, folks. That makes a big difference. Try it again. There's my population curve coming in. Second trace. Second trace. Intersect command. Enter, enter, enter. 20 point, about 20.7 years after 2000. So you could say during 2020. Yes, check.
Sorry, can I see your white and close it?
Sure. Who's next? Questions?
Oh, you do 34.
Yeah?
Get out of here.
All right, it says the number of grams of carbon-14 denoted C present in a certain substance after T years is given by C of T equals yada, yada, yada. Use the equation to estimate the half-life of carbon-14. So if we start with 20 grams, which you can see, what would a half-life represent? Decay down to how much? 10. So that's what I'm going to be solving. Now, anybody recognize or know the significance of carbon-14 decay? We use it for carbon dating. So, how old can we date things using carbon dating? Like 100 years or like thousands of years? Thousands of years, right? So I'm gonna make my X then go to like 10,000 or something. Sound okay there? My Y min goes 0 because it's a decay situation. We'll start at 20. So there's my 10 grams and my decay curve. Second trace, intersect command, enter, enter, enter. 5,700 years. So again, knowing something about what carbon-14 was going to be used for was kind of helpful in picking a window there. But you could have eventually figured it out just by picking progressively bigger and bigger X's. Luke.
I'm Zach.
Zach.
Can you do number 6?
Sure. So it says the population P in millions of people of New York State 2 years after 1900 is modeled by this equation. Was the population in 1850? So how many years after 1800 is 1850? 50 years. So I'm just going to be plugging 50 in for T. I'm going to just do this the sneaky way. 19.875 plus 57.99, oops. $57.993 e to the ugh, come on. Negative 0.035005 t. All right. So vars, y vars, function y2. So I'm going to plug 50 in for that. I'm just going to use my calculator to handle all the heavy lifting. So I have about 1.79 million. Remember that the P of T is coming out in millions. So 1,790,000. Said, what will the population of New York be in 2010? So how many years is 2010 after 1850? 210. So I'll do the same thing here. So about 19.16 million.
How did you get to the Y2 in the equation thing?
Vars, y vars, function,
Okay.
and then picked y2 from the list. And the last one, what is New York State's New York City's maximum sustainable population? I'm sorry, New York State's. That's going to be, I recognize this is a logistic function. Logistic function has an upper bound and lower bound. The lower bound is always at 0, and the upper bound is always at the numerator. So 19.875 million would be the upper bound. That would be the maximal sustainable population. Cool? All righty. I saw some other hands that kind of went up and then went down at other points. Dude, Arya?
Can you just quickly explain that and know like what to make the y and x axis?
I didn't graph anything on that problem.
No, just like for the other ones. Like,
It depends on the problem.
so you make the big one as the y.
The big one, what do you mean the big one?
Like if the population is a million, you change the y max.
Whatever value you're solving for needs to be between your y min and y max. Is that what you're asking?
Yeah.
Okay. Check.
Sorry.
Okay. Zach?
32.
Okay, 32. All right, the half-life of a certain radioactive substance is 65 days. Suppose there's 3.5 grams initially. Express the substance as a function of time, and when will there be less than 10 grams? So for a half-life, I'm still going to be using that population model. So 3.5 is my initial. For half-life, I remember that R is always negative 50. And then the T, since it's going to take 65 days for a half-life, I do 1/65 of a half-life in 1 day. Where T is in days. So that's part A. Part B, it says, when will we get less than 1? So let's think about this for a moment to sensibly pick our window. So we start with 3.5, and then we go down to 1.75 after 65 days. 65 more days will be less than 1, right? So I think that for my window going on the X's, I would want to do something that's bigger than 100. So I'd probably go to 150. So do 0 to 150 maybe. And then we're starting at 3.5 and going to 1. So 3.5 could be my max. I'll pick something bigger than that that's a round number, so I'll just do 5. So there's my curve. There's my intersection. Second trace, intersect command, enter, enter, enter. And I got about 117.5 days. Is that okay, Jack?
Yeah.
What?
I would have been something wrong with that.
Is what you typed in?
Yeah. Is that a negative point, or is it just positive?
Positive.
Yeah, I'm not sure.
Okay, maybe we can take a look at it later and
Okay.
figure out what's going on.
Oh,
Zach.
And you do 76.
76. So it says my directions here are to expand. First thing I do is look for a quotient property. I don't see one. Product property. Don't see that. Power property. And I'm done. Cool? Okay.
If you wanted to, could you drag it out by 1 over x squared and then you quotient of x?
You'd end up with 0 minus 2 log base 2 of x, which is exact same thing.
You'd still get it.
You'd get the same thing doing it that way. Sure. Alexis.
Can you do 92?
Sure. So we're going the reverse direction. So first we're looking for power properties. I see 2 of those. I have to make sure that I'm careful when I'm applying that power property because the power is going to apply to everything inside that logarithm. Next, we look for product properties. I see 1 of those with the plus sign. And then I just combine my like terms. And I'm good. Alexis, you happy with that? Yeah, no problem. Just got to be careful with your exponent rules there, right? Okay, last call on questions. All right. Then today we start chapter or section 15.4. Which is great because now we can stop dancing around this existence of logarithms and start using them to do some solving, which like, woo, it's about flipping time, right? So one solving tool that we can use are these one-to-one properties. So the first one says for an exponential function, if b to the x is equal to b to the y, then x is just equal to y. Well, that should be kind of common sense. We can say this same thing about logarithms. So for a logarithmic function, if we have b to the, or log base b of x equals log base b of y, then we can just say that x is equal to y. God bless you. You're welcome. Okay. So, we're going to do some solving here. First thing up, we have 12 times 3 over 2 x to the 3 over 2 to the x over 5 equals 27. What's the first thing we should do here? Grace. What? Oh, sure. What should we do first here?
Graph, find the intersection.
We're not graphing and finding intersections anymore. We're gonna do this algebraically, although if you're taking an ACT and that's the route you wanted to go, that's a perfectly reasonable thing to do. But the point here is we're trying to do this algebraically. Yeah, divide by 12. Important, we must do that before we start logging stuff. My little loggers. So 27 divided by 12 reduces down to 9 over 4. Okay. Now what? So there's two separate routes you could go. So one is you could rewrite this with a common base. So notice that 9 over 4 is the same thing as 3 over 2 squared. And then we can apply the one-to-one property, and we get 10. Everybody's okay with that? The advantage here, very easy, right? No calculator necessary. Everybody okay with that? Disadvantage to doing it this way. It may not be easy to be able to rewrite with the same base. That might be very complicated or not obvious at all in some cases. But in this case, super obvious. Well, or at least reasonably obvious. Okay? The other suggestion here was to use a logarithm. Great. What log do you want to use? Base 1, 2, 5, 8, 16, e, square root 2? What log base do you want to use here? What one? Log base 3 over 2. For optimally, again, you could use any log base here, but if you're looking to make your life as simple as possible, you'd want to match your exponent base and your log base. Somebody's upset. Hi, Miss Lytle. How are you? You're welcome. Jordan, it's for you. You're welcome. Okay. And then my last step would be to multiply both sides by 5. And then it's calculator time. I'd like to point out that, like, conceivably, you could do log base 3 over 2 of 9 over 4 by hand, but more often than not, if you're choosing to go this route, you'd probably not find an easy way to do that. Or you could have done it the other way. But you'll notice I get the same value here, right? What do you guys think? Okay? Either method is fine. They are doing the exact same thing. It's just like a different way of kind of conceptualizing the exact same result and the exact same process. And really, like, it is still the same. All right, let's do another example. So we have 14 times 1/3 to the x minus 1 is equal to 126. First thing you guys want to do is divide by 14. Very good. Okay, what do you want to do from here? You could do a log, or what's the other method that we've talked about? We could rewrite this with the same base. Is it easy to tell what that same base would be? It's a little bit trickier here, right? it is possible. It's -2. That's a little tougher to see right away, right? The negative makes the reciprocal, and then the reciprocal is 3, and 3 squared is 9. That's a little tougher maybe to see, but still doable. Here, if we wanted to use a log, which log would we use? Log base 1/3. So we got to be a little bit careful. I know what you meant, but when you say log 1/3, most people when hearing that would say, oh, log of 1/3, not log base 1/3. So you have to be a little bit careful in how you're communicating that. Now I knew what you meant because I've been doing this for long enough that I know that that's what students are going to say. But, you know, somebody that's a little bit more I don't know, picky would be like, nope, that's wrong, even though it's like, oh, that's what I meant, but it's like, not what you said, you know, but I'm not that kind of guy. And then we just add the 1 over, and we go to our calculator. Again, you could do log base 1/3 of 9 by hand, but my suspicion is if you chose to go the logs route, you wouldn't want to, you either wouldn't want to do it that way or you couldn't see how to do it that way anyways, because if you're able to do log base 1/3 of 9 by hand, you could have just done the other way. You know what I mean, guys? So far, so good. Not a big deal, right? Well, Mr. Kulik, how does this get harder? Well, let's show you an example of something that's a little bit more complicated. Let's take a look at this one. Oh, Boise. There's probably like 3 things on this that are like, oh, I'm not sure what to do with this. Anybody take a stab at those 3 things that make this problem a little bit harder than the previous one? There's a fraction. Great. What else? You have x in 2 different locations, and we have a negative exponent, right? Now, we're going to take care of each of those complications one at a time. Which one do you suppose we're going to take care of first? The fraction, yeah. Because that's an easy problem to solve. Boom. Done with that. Everybody cool? Multiply both sides by 4. What are we going to take care of next? The negative exponent. Good. How are we going to take care of that? Well, if you make the reciprocal, we're back to fraction town again. I'd prefer not to visit there. This is what I'm going to do. Multiply both sides by 3 to the x. Wait, what? Why do you want to do that? So when I go ahead, I distribute that through. When I have an exponential times another exponential that has the same base, we add their exponents, right? Note that I wrote x minus x instead of x plus a negative x. You guys are cool with that, I hope. So I get 3 to the 2x plus 3 to the 0 equals 8 times 3 to the x. And what's 3 to the 0? 1. So I'm going to go and move everything onto one side now. What kind of an equation does this remind you of? Quadratic, yeah. I notice I have 3 terms. Note here that, let's say, we know x to the AB is equal to like x to the A to the B. So I'm going to use that same idea here to think about 3 to the 2x as 3 to the x squared. Is everybody cool with that idea? So this is decidedly quadratic. This is how we're going to take care of the x's in more than one location, because we know how to solve quadratics. What are the two primary methods we use to solve a quadratic? Factoring and the quadratic formula. In this case, which one would I use? I'd use the quadratic formula because there are not two numbers that multiply to give me 1 and add to give me -8, right? Now, it's not unfair to want to start by trying to factor, since you see the leading coefficient is 1. If it was going to be factorable, it would be an easy thing to factor. So let's see, what do we have here? We have 8 plus or minus. 64 minus 4 is 60. And let's see, 60 is 4 times 15, right? Why would that be helpful? Yeah, because the square root of 60 is then square root of 4 times the square root of 15, or just 2 square root 15. And that allows us to dump off the fraction, which is always kind of helpful. But guess what? We're not done. Why not? What variable are we supposed to be solving for? X. What have we solved for? Y. So we now just go ahead and put our 3 to the x back in. And I'm going to write two separate equations because the plus or minus is giving us two separate answers, right? Everybody cool so far? All right. How do you want to solve these exponential equations? Probably want to do a log here, right? Very unlikely you'd want to try to rewrite these with the same base. Although, hypothetically, if you did do that, that same base would just be, you'd have to do that, which is exactly the same thing we're going to get when we take the log to both sides. So it's like, not so surprising. Which log am I going to use? I've kind of given away that already, huh? Yeah, log base 3. So that's just like a hypothetical there that I wrote there in the red. So calculator time. Math. That's the wrong button. Math. Log base 3. And then 4 plus 2 square root 15. Oh my goodness, guys. That's just 4 plus the square root of 15. Sorry about that. Yeah, I didn't reduce the... It's like, that didn't look right. There we go. So I get about 188 on that. And then if I do this the other way, and I type that into my calculator again, I get about negative 188. Now here's a question for you. Well, I always get two answers when I do this. When I solve this kind of an exponential equation, I always get two answers. No. Why not? It's actually two different things that could happen. The first thing, when we get to the quadratic part, how many solutions can a quadratic have? 0, 1, or 2 solutions. So just from that, you could have 0, 1, or 2 solutions. Again, when we're dealing with an exponential equation, in solving for x, we're only talking about real numbered solutions. If you get an imaginary, you're just donezo, okay? But there's another place where we could get 0, 1, or 2 solutions. So even if we get that far and we get 2 solutions, from the quadratic, doesn't mean we're going to get 2 solutions for the exponential. What else could happen? Yeah, so remember, we can only take the logs of positive values. So if our one or more of our solutions from the quadratic was negative or 0, those things are going to be undefined when we try to take the log of them, and those ones will result in no solution for the exponential. So you could have one that's positive and one's for negative from the quadratic. That's going to give you one answer for the exponential, for example. Is everybody cool with that? I just want to make sure I touch on that. Somebody's always confused when they start getting less answers than they expected doing these sorts of things. So I just want to make sure that we're clear about it. Okay, that's about the most complicated log or exponential situation we can kind of run into. Let's look at some logarithmic equations then. Okay. Let's say we have this logarithmic equation. What's the first thing we want to do? What's up? Yeah, that's what I would do. Divide by 3. Okay. What's up next? Two algebraic options. Probably the easier of the two would be to try to cancel the logarithm. What operation is going to cancel a logarithm? Exponent base. Which base would I want to use here? 10, because I want my exponent base to match my logarithm. And again, I like to write my exponent base really big on my paper, so I'm not confused whether I'm multiplying or using exponent base. Hi!
What can we get you? Coffee cart.
Ooh, let me look at, do we have a donut selection?
You could multiply your calorie intake right now.
Oh boy, I can't.
Let's do a little experiment while he's out. What kind of donut do you think he's going to choose? What kind of donut do you guys see?
How many options are there?
There's not a lot left, but what kind of donut do you see?
I think jelly though.
Let's see what it's like, what's your favorite donut? We were just discussing. What kind of donut eater you are?
I like the I like the, not the cakey ones, but kind of the fluffy ones.
Yeah.
Fruitier?
No.
Like that, but lighter.
Like this is the cake kind.
Yeah.
That's like when you break it apart, it's like a piece of cake. The other ones are like the deep fried ones or whatever that aren't baked. And if it's like that, it doesn't matter whether it's like cinnamon sugar or glazed or sprinkles with frosting. Yeah, but I don't like Krispy Kreme donuts. I find them like too rich for me or something.
Enjoy your donut.
But hey, thank you. I appreciate it.
Don't forget about lunch.
Yeah, I won't be there.
Thank you.
Hi, everybody.
We're back.
Welcome back.
We get a taste test of the donut right now? ASMR.
For me?
What's the rating?
Out of 10.
They're gone, so you can be honest.
Give me a log. It's bad, you should say. Give me a log that equals your...
It's like a solid 8.
Log base.
Yeah, log base 10 of 10 to the 8. All right. So if I do that, I end up with x squared is equal to 10 squared. So x has to be plus or minus 10, right? Are you happy there? What's the other way you could have attacked this? Could use the one-to-one property. How do I rewrite 2 as a log base 10 number? And then you could do the same thing and do... Either way is accomplishing the same result. Again, doesn't matter to me. Whatever you're more comfortable with is fine. However, we're not done. All logarithmic equations need to be checked because you can end up with extraneous solutions. Fortunately for us, the check is very easy. All I need to check is that when I plug this back into the original, I have to make sure that I'm not going to get a 0 or negative inside my logarithm. Need to make sure everything inside my logs is positive. Now here, when I'm plugging into x, it's x squared. So like everything's going to be positive no matter what. So it's fine. Both of these work. But that need not always be the case. Everybody's cool? All right. Mr. Kulik, that one, pretty easy. Do the logarithmic equations get harder? Well, I mean a little bit, but not like terrible. All right, let's take a look at this one. Oh, boy, is it? So, a couple of things should stick out to you right away that make this one quite a bit more complicated than the previous one. The major problem here is I have x's in multiple locations, right? That's the major concern here. Lots of logs, it wouldn't be a big deal if they were just logs of a number because they're just decimals then and you just grind through it the same way as the previous problem. Here, because we have x's in multiple locations, we got to be a little bit more careful. What's the first thing I'd want to do here? Use the properties, Priscilla. Great answer. So the property she's talking about is the product quotient power properties. Is what she's talking about on the left-hand side. Which one of those could I use? Product. Because of the addition symbol? On the right-hand side, which one could I use? Power, because of the exponent or the coefficient in the front. Everybody's happy with that? Notice here, this is now screaming at us to do our one-to-one property, where we can just drop the logarithm since they're both log of A is equal to log of B, right? And I'm going to FOIL this out at the same time. While I did that, is that okay with everybody? What are you noticing? Hi, Vlado. Who are you looking for?
Dominic. Thank you. Sorry.
No worries. What do we have now? Quadratic. Yes, subtract x squared from both sides. Solve the quadratic, it must equal 0. Okay, two major methods to solve the quadratic are Factoring and quadratic formula. Which one do you want to do here? I would do the quadratic formula here. For the record, this does factor, but because the leading coefficient isn't 1, the factoring is like the long factor by grouping method, that if you want to do that, that's fine, but it's probably the same amount of work as the quadratic formula is, which I know is guaranteed to work. I'm not guaranteed the factoring is going to work right away. So that was my motivation for doing that. And everybody has the quadratic formula memorized, right? At this point. If you don't, you should. All right, so I have 25 minus 16, that's 9. The square root of 9 is just 3. So 5 plus 3 divided by 4 is 2. 5 minus 3 divided by 4 is 1/2. Am I finished? No! Why not? Gotta check. All right. So if I go and I want to check x equals 2, I got to go all the way back to the beginning. 3 times 2 minus 2 is positive. 2 minus 1 is positive. 2, positive. That one's good. That's all that I need to do for my checking. I don't actually have to plug everything in and make sure they're equal. This is the minimum amount of checking. Obviously, I could do that, but like, who has time? All right, the 1/2. 3 times 1/2 minus 2 is negative. I stop. That one doesn't work. I'm done. How do you guys feel? All right, we're gonna stop here.
I forgot how to do all of those.
At this point, you guys should be able to do, what is it? 99 to 130 is the stuff from this section. You guys can clear your stuff.